Hey everyone, and welcome to another video on graphing equations and functions, this time absolute value functions, so let's do it. Alright, so we've already graphed a whole bunch of different equations and functions, but to date, they've all either been lines or these U-shaped parabolas. And like we said before, there are so many different types of equations we can graph, and there's no way we can cover them all, but I do want to investigate another family of equations involving absolute value. And here's our baseline equation, y equals the absolute value of x. And we want to graph all the ordered pairs that work for this equation, whether you consider them solutions to an equation with two variables or input-output pairs to this rule or function involving an input and an output. And our strategy is going to remain exactly the same. Because there are two variables in this equation, there are going to be infinitely many ordered pairs, and we couldn't dream of listing them all or graphing them all. So what we're going to do is we're going to find some ordered pairs, and we'll graph them, and hopefully we can find some sort of pattern, and then extrapolate that pattern to draw a graph, which represents all of the ordered pairs for this equation. So, why don't you pause the video, find a collection of ordered pairs, graph them, and hopefully we'll find a pattern. Remember, we like to start using 0 as our first x value, and then branching right and left of 0 using positive and negative x values, and a wide range to get the best picture of this graph. Alright, now that we've graphed these ordered pairs, it kind of looks like we got a V-shaped sort of graph going on. Now, again, there are going to be infinitely many ordered pairs for this graph, and we only found 9 of them, and we only used nice integer inputs. We didn't use any fractions, we didn't use any decimals at all. So before we go ahead and actually connect them and extrapolate and draw this V-shaped graph, we want to make sure that we got it right. So let's use a piece of graphing calculator software for the computer just to make sure we did it correctly. Alright, as you can see, we've got a set of axes here. In the upper right hand corner, we've got the x and y values for ordered pairs for our equation y equals the absolute value of x. What we're going to do is we're going to cycle through x values from negative 12 to positive 12, and what the graphing calculator is going to do is going to find the corresponding y values, so the ordered pairs, and it's going to graph them at the same time. So let's see what happens. As you can see on the right, we've got way more ordered pairs than we could ever want to do by hand, but as the graphing calculator graphs them all, we see that the sketch we came up with by hand looks to be exactly what the actual graph looks like when we use tons more inputs. So we can confidently say that that V-shape is the graph and is the representation of all the ordered pairs for the equation y equals the absolute value of x. Alright, back to our hand-drawn graph. Now that we know that we can extrapolate this pattern to draw our graph representing all the ordered pairs for y equals the absolute value of x, let's go ahead and do that. Remember that since these ordered pairs are going to continue on in this fashion forever, we want to put some arrows at the end of these graphs. Now note, if we just look at the non-negative inputs on the right side of the graph, look how tempting it would have been to think that this graph was actually another line, like before. But of course, once you use some negative inputs, it became very clear that this graph was actually V-shaped. So just another example of why it's really important to use both positive and negative inputs when piecing together a graph. Another interesting thing about this graph is that note that once again, this V looks symmetric over the y-axis, over the place where x equals 0. If we draw that line right there, this graph on the left and right side looks like a mirror image of itself. Now, let's think. Why might that be the case? Well, note that when we take the absolute value of a number, or its additive inverse, we get the same thing. For instance, the absolute value of 3 is 3, but the absolute value of negative 3 is 3. The absolute value of 4 is 4, and the absolute value of negative 4 is 4. So, no surprise that we end up with a symmetric graph in this case. Alright, let's try graphing another equation in the family of absolute value graphs. Here we've got y plus 3 equals the absolute value of x. Now of course, the only difference between this equation and our original baseline equation y equals the absolute value of x is that the y has been replaced by a y plus 3. And I wonder, what's the effect going to be on our graph? Now a quick flashback, we had a similar manipulation on one of our graphs in the previous section, where we started with y equals x squared, And by replacing the y with a y plus 4, that shifted the graph down 4 units. Well, let's see what happens in this case. Once again, before finding ordered pairs, it's probably best to put this into y equals form. So we've got y equals the absolute value of x minus 3. Once again, I would center your inputs around x equals 0 and branch to the left and right of there using both positive and negative inputs. So why don't you pause the video, find some ordered pairs, graph those ordered pairs, and if you find a pattern, feel free to connect the ordered pairs, extrapolate, and create your graph representing all the ordered pairs for y equals the absolute value of x minus 3. Alright, it appears that we got another one of these V-shaped graphs. Now, we didn't talk about the x or y intercept on the last graph because it went right through the origin. So the x-intercept was 0 and the y-intercept was 0. What about in this case? The y-intercept is pretty easy to see from our graph, and it happened to be one of the ordered pairs that we found earlier. It also appears that we have two x-intercepts because our graph hits the x-axis twice, at the point 3, 0 and at the point negative 3, 0. So we'd say our x-intercepts in this case are both negative 3 and positive 3. Once again, we got a graph that is the exact same shape as y equals the absolute value of x, but it appears that this graph has been shifted down 3 units. Now maybe you predicted that before, and using the graphing calculator app again, we can see that replacing the y with a y plus 3 had the effect of shifting our graph down exactly 3 units. Alright, let's do another example. In this one, let's graph all the ordered pairs for the equation y minus 6 equals the absolute value of x. Of course, the only difference between this and our baseline y equals the absolute value of x is that we've replaced the y with a y minus 6. Now, quick flashback, earlier we did a similar manipulation where we replaced the y with a y minus 2, and that had the effect of moving our graph up exactly 2 units. So let's see what happens in this case. Now, why don't you put this into y equals form, please find some ordered pairs, graph those ordered pairs. If you see a pattern, feel free to extrapolate and then extend your graph, find your x and y intercepts, and when you're all done, we'll reconvene. Alright, again, we got a very similar looking V-shaped graph. The y-intercept is 6. Since this graph never hits the x-axis, there are no x-intercepts, and it looks like the exact same graph as y equals the absolute value of x, but shifted up exactly 6 units. And if we look at the graphing calculator, we see that replacing y with a y minus 6 had the effect of moving our graph up exactly 6 units. Alright. Now let's graph the ordered pairs for y equals the absolute value of x plus 3. Now, of course, the only way that this differs from our baseline equation y equals the absolute value of x is that now we've replaced the x with an x plus 3. Now, a flashback to before, we had a similar manipulation where replacing the x in the equation with an x plus 7 had the effect of moving our graph to the left 7 units. So, going back to this equation, let's see what happens to the graph as a result of replacing the x with an x plus 3. Now, since we're already in y equals form, why don't you find a whole bunch of ordered pairs, graph those ordered pairs, connect and extrapolate your graph, find your x and y intercepts, and then we'll reconvene and discuss how this graph differs from just y equals the absolute value of x. Once again, we get a V-shaped graph. We see that our y-intercept is 3, and we have just one x-intercept, and that's negative 3. And this graph looks like it has the exact same shape as the graph of y equals just the absolute value of x. But of course, this one looks like it's shifted to the left 3 units. And when we use our graphing calculator, we see that yes, when we replace the x in our equation with an x plus 3, the effect is that it moves the graph to the left 3 units. If I were to add something here, Note that this graph is symmetric about the point where x equals -3. So it makes sense to me when I see this x plus 3 in our absolute value bars that it might have been smarter for us to center our x values around -3 and then go to the left or right from there. Alright, let's graph all the ordered pairs for y equals the absolute value of x minus 6. And right away, I'd like you to pause the video, find some ordered pairs, graph them, and sketch what this graph should look like. And please make sure to find the x and y intercepts too. And so we see, we get another V-shaped graph. The y-intercept is 6, the x-intercept also happens to be 6, and this graph is moved 6 units to the right of our original y equals the absolute value of x graph. Of course, in this case, maybe you notice that it's smarter to center your inputs around 6 and then branch out from the x value of 6, both to the right and the left. Here's an even tougher example. Here, we've taken our original baseline equation, y equals the absolute value of x, and we've replaced the x with an x minus 2 and the y with a y plus 5. Now maybe we can predict what effects these two manipulations are going to have on our graph. But nonetheless, I would like you to take this equation, put it into y equals form, and then find a whole bunch of ordered pairs and sketch this graph, making sure to find the x and y intercepts. And then when you're done, we'll reconvene. Alright, and so we get, again, another V-shaped graph. The y-intercept is -3, the x-intercepts are 7 and -3. And we can see that replacing the x with an x minus 2 had the effect of moving the graph to the right 2 units, and replacing the y with a y plus 5 had the effect of moving our graph down 5 units. So no different from what we did before. We've just combined replacing x, which moves our graph left and right, with replacing y, which moves our graph up and down. Now, while we just did those manipulations to an absolute value graph, we could do the exact same manipulations to one of the parabolas we did before. Here, if we replace x with x minus 2, it still moves the graph to the right 2 units, and if we replace y with y plus 5, it still moves the graph down 5 units. So those same equation manipulations are going to have the same effects on the graphs no matter what graph you start with. Alright, last example. Here, let's try to graph all the ordered pairs for y minus 7 equals the absolute value of x plus 4. Now compared to our baseline equation, y equals the absolute value of x, we've replaced x with an x plus 4, and we've replaced y with a y minus 7. So I urge you to anticipate what effects these two manipulations on the equation are going to have on the graph. But nonetheless, I'd like you to pause the video, put this equation into y equals form, find a whole bunch of ordered pairs, graph them, sketch your graph, find the intercepts, and then we'll discuss the difference between this graph in black and our original y equals the absolute value of x. Alright, so here's our graph. Of course, it has the exact same shape as y equals the absolute value of x, but replacing the x in the equation with an x plus 4 had the effect of moving our graph to the left 4 units, and replacing the y with a y minus 7 had the effect of moving our graph up 7 units. So again, just combining a horizontal shift by replacing x with x plus 4, and a vertical shift by replacing y with y minus 7. And again, these manipulations are going to have the exact same effect on the graph no matter what graph it is. Here's our standard parabola, y equals x squared, and replacing the x with an x plus 4 still has the effect of moving our graph to the left 4 units. And replacing the y with a y minus 7 still has the effect of moving our graph up 7 units. Alright guys, that's it for this video. I hope you found it helpful, and I hope you enjoyed.